or machine learning model using the graph-based method. So because we can have different types of nodes and heterogeneous graphs. We use our tools a lot in user modeling, especially when it comes to privacy safe user modeling. And then also like in different ML efficiency, like machine learning efficiency for sampling the data and for like other applications like that. We use like some of these tools. We focus mainly on scalability of our tools and like the speed and ease of use, but also more recently on the explainability and stability of the tools. And I won't actually cover those, but I just wanted to give you a flavor of the type of research that happens in the team. So like maybe a couple of slides about the applications to give you a sense, because I'll switch to talk about the abstract problems next. In the context of detecting spam, fraud, or abuse across many products like ads, YouTube, Android, and so on, we use graph-based learning in two different ways. One is what we call semi-supervised learning, or like simply label propagation, where we have some data and some labels on some bad actors, for example. We discover new links between these bad actors and then like propagate the information. But then we use also not only the graph, also the metadata on these data sets. We also use graphs in an unsupervised learning manner in anomaly detection, for example. One application or like one example is where we detect like relations between different type of entities, and then we use density clustering or finding dense subgraphs to identify malicious behavior. Another big application area is actually in privacy, where we actually model many user modeling problems we have, or like interactions of users with some other entities like domains or clicking users on ads and so on. So like the user modeling problem there can be formalized as a bipartite graph, and then processing this bipartite graph in a privacy safe way, for example, is an important area for us in terms of applications. We can also mine this bipartite graph. For example, instead of like tracking relations of like individual users with the domains or with like ads or with other entities, we can go to a higher level and use interactions of clusters of users. And that clustering, these bipartite graphs can be used to develop more privacy safe, basically data mining. And like, yeah, in the context of clustering and privacy, we either develop differentially private clustering techniques that achieve like better level of privacy, but yeah, like the scale is like we are trying to develop more scalable tools for that. We also use minimum size clustering to provide some level of anonymity, or what we call label differential privacy in different applications. So I mentioned a number of papers like that we have written in these topics, and we also compare trade-offs of basically both like applications of clustering in achieving label differential privacy and k-anonymity, and how they relate to each other in terms of the utility. So other applications that I just mentioned is like in enriching other machine learning models, for example, in feature engineering, or in adding relational data to our machine learning models. What we call efficient, where we either minimize the communication overhead in a distributed learning task. For example, in Google driving directions, we use like some of our clustering tools to decide what part of the data is handled by each server. Or like in the context of active learning and data efficiency, we have the representation selection like problems that can be formalized as independent sets in a graph. This is just like very high level, telling you some applications. So now I'm done with the very quick intro of the graph mining projects. Now I'm going to give you just give you a survey of like 3 lines of work that we have done recently that have a flavor of both theory and practice. So like I chose these topics These are the topics that we have done some theory and they inform practice, or we have done some practical, we have some empirical observations and we put like a theoretical model on top of it. So the first one is about distributed graph computation models and what I call AMPC versus MPC model. So when we want to model, like we want to discuss a distributed model that can formalize what we do like in computation in MapReduce and like GRaph in particular and Hadoop. The theoretical model is what we call a massively parallel computation model or MPC model. So a formal definition of this model is given an input size n and data, like let's say we have m machines, each with some space s. So we say like the total size of the data is maybe m times s, but s, the space on each machine should be sublinear or maybe n to the epsilon, like given the total basically like available memory on each machine. So the computation in the MPC model happens in synchronous rounds. So it's not asynchronous, it's like synchronized. And like the model is in each round of computation, machines receive maybe some data from previous rounds. Then they have some data, they perform some computation, and then they communicate, send messages to other machines. We also put some condition, like a restriction on the amount or the number of messages that each machine can read or write. And that should be restricted as well. Like it's not basically unlimited. It's like also related to the size of that machine, which is n to the epsilon again. So this model, MPC model, was introduced in a SODA paper like 10 plus years ago. And basically, like over time, better and better algorithms have been developed for different graph mining tasks, algorithmic tasks. Most of these tasks can be done in either logarithmic or basically super constant related to the like log of the size of data. So for example, the most popular application in our case is clustering and connectivity. For connected components, the best algorithm is like an algorithm with log of d, which is the diameter of the graph, plus log of n. Yeah, so for matching, there's a square root of log n approximation, like an algorithm that solves it in square root of log n and so on. So now, one thing to say, emphasize is that the model is actually appropriate to for like graph computation, especially in what we call preemptible resource settings, where we want to develop like an algorithm, like algorithms that are like good for like that achieve like good fault tolerance. And what we observe is that in an environment like where like many engineers are trying to use like machines that can be also shared with some production tasks, part of the resources are actually available at very low cost, but they can be preempted. So like these type of models are suitable for that. But then at the same time, MPC model has some restrictions, which is basically the I/O should happen all at the same time. And this actually gives us like restrictions on the number of, on the type of computation that we can do. And like in some cases, the number of rounds of computation being super constant is like a deal breaker. So what we have introduced as a theoretical model like 3 years ago is what we call adaptive massively parallel computation model. So this is actually inspired by some of our empirical studies that I'll mention in the next slide. But let me first give you what is the model. The model is basically similar to MPC, but it's amended by a distributed hash table service, where in each round of computation, we have similar restrictions. Like each machine has like sublinear size that it can handle. But what happens is that instead of sending messages to other machines, the messages that, or the computation that each machine has is written into a distributed hash table service. And then each machine can read from this distributed hash table service in a random access model. But then we have still restrictions on the number of data like points that each machine is going to read. So, and we have a similar like restrictions on the communication. So this will make the communication model and the computation model much more flexible and still interesting and relevant. So before telling you about the theoretical results we have on the distributed hash table service model, let me emphasize that before developing the AMPC model, we developed actually several like tools, for example, solving connected components, for solving what we call hierarchical clustering or affinity clustering. We had like techniques to use distributed hash table service to solve these problems very efficiently. And like this inspired us to put like a computation model on top of it. And then more recently in this SPOT 2019 and VLDB 2020 or 2021 paper, we have now developed algorithms that can run in constant number of rounds as opposed to logarithmic number of rounds for many of these graph problems. Like the most important one for us is clustering or connected component that goes also from log of d to order of one. And like in practice, this improvement is also like not only from like log of d to order of one, we see like it's a big improvement. I'll show you one example. So this helps us also go beyond some of the lower bounds that are conjectured, at least for the MPC model, like the two-cycle conjecture that you may have seen. And yeah, like there's more to be done in this space, but just to give you a little bit more about why we think AMPC model is actually a realistic model. One question is if the, hello, so just to confirm, you hear me well?
I think, yeah,
because I don't see you. Yeah, excellent. So one question is if the assumption for the random access on the distributed hash table service, basically a reasonable assumption. And that's something that we confirm using this RDMA hardware with very low latency. We can have this random access in a distributed way. And that's something that, yeah, like we use, and like it's also available on the cloud. Yeah, there are like different parts of the application. But one important thing is that it does allow us again still to have fault tolerance in a very effective way, and that's like a very important part of having like a good distributed system. And so on. Yeah, basically there are like, one question is what is the implementation of the distributed hash table service? And that's also like a well-studied problem. So with that in mind, we also implemented these algorithms in the AMPC model using basically an implementation of Flume or MapReduce, and also distributed hash table service at Google. And we see that, for example, for spanning forest or independent set, the number of rounds of computation goes from like tens of like 30 to 80 here to 5, or like 8 to 14 to only 1 round of computation. And that gives us like good improvement in the running time. And these are like empirical studies that we did for a graph that's publicly available and basically has 200 billion edges. So I'm done with the first part. So like my message of the first part is that the MPC model is an interesting model to study. There are actually like another paper that also proves some lower bounds now, but yeah, like there are more problems or that we can study in the MPC model. For example, the hierarchical clustering problem that I'm going to tell you more about. Now I want to tell you about some recent developments in building these large graphs, which is yeah, like an important part of the library. So first of all, what do we mean by building a graph learning problem? In many cases, we don't have, so like maybe in, I should say in half of the applications that we work with, we have a natural graph that can be explicitly basically built. But in maybe half or even more than half of the applications that we work with, we don't have an explicit graph. So in order to to formalize our problem as a graph mining problem or a graph learning problem, we have to also build this nearest neighbor similarity graph. The problem is well defined, and you've seen maybe, so like we are given a data set with some like similarity measure between points, and our goal is to basically discover these edges. But we don't want to do like n squared number of computation. We want to like do sublinear number of pairs that we examine. And the examples of the similarity measures that we care about are Jacquard similarity, or cosine similarity, and so on. So like, why do we want to build these graphs? So there is actually like a good discussion about why should we, when you have data that's not in a graph format, what's the advantage of translating it into a nearest neighbor graph and analyze it? There are like several answers. There is the computation reasons that by pre-computing these nearest neighbors, we can actually use the nearest, the neighborhood information in enriching our basically computation in the next rounds. There are like, and then like, as we'll see, there are several applications of like data mining that like, if we build these graphs in a smart way, we can do much better. So like the clustering application is actually one of them that I'll also elaborate in the last part. Another major application here is like in label propagation, or like when we have labeled data and we want to do semi-supervised learning. Basically, by building these graphs ahead of time, we can basically propagate information over edges that are pre-built and maybe also dynamically built, but like in a formal way, we can use the structured information now on the graph. On the clustering side, in connected components, what we call affinity clustering and hierarchical clustering, you've seen applications of like the advantages of like building the graph ahead of time, and I'll say more about this. So in terms of the tool set that we have built for this, we have like a two-stage system that we call GRAIL for building these similarity graphs. In the first stage, we find actually candidate pairs of points that are basically good, that we have an educated guess of like them being related because they share features, for example. So over there, we either use locally sensitive hashing or what we call sorting LSH technique that I'll actually talk about. And in the second stage, we may compute something simple like Jacquard similarity, or we can go to a model training, like a learning model, like a deep learning model or a random forest model or something like that, that can be actually learn on a training data. That's how we define what we call graph learning or GRAIL. There is an empirical paper by the team about the GRAIL system itself. So today, what I'm going to tell you more about is the algorithmic technique that we have used like to improve the graph building part or the first stage of this process. But it's important to keep in mind that we may build these graphs for a downstream task of, for example, learning a similarity score on the candidate pairs or on solving another problem like label propagation or clustering. So the first technique is locally sensitive hashing, which is what like we have learned a lot. I mean, I have learned it from Piotr here, and yeah, like there is a good survey by Alex here. So the idea of locally sensitive hashing is to find basically mappings of points that put like similar points or like close points into the same bucket. So it's a hashing technique that when we do this locally sensitive hashing, one challenge that can show up is that the points like on the dense part of the data can result in basically large buckets. And if we have large buckets, when we do locally sensitive hashing, we may need to compute many pairs of distances like in each bucket. And that's like that can be a problem. So one way that we deal with this, at least in practice, and as I'll show, like it can help us, is like what people call like forest LSH or what we call sorting LSH, where basically we, the idea is just do like many of these hashing, like, and then build a vector and then do a lexicographic sorting of these vectors. And the sorting part can be done in parallel, like in a distributed way, very fast. And this will help us, the sorting part give us like a way of bucketing the data, and we have like more, we can manage the size of these buckets by just cutting or like finding consecutive chunks of the data on this sorting part. So this will help us improve the practical, at least empirical performance. But one thing that we have done recently, and we see like big advantages of using, is what we call two-hop spanners in building graphs. So even when we use sorting LSH, we can have like big buckets, and like in order to capture a good coverage, we may end up like computing many pairs. So what we observe is that for many tasks that we build these graphs for example, for clustering and label propagation and so on, we don't have to construct a graph by itself. What we can do is maybe we can build a two-hop spanner version of the graph. The first part, like this idea of two-hop spanner was used in a paper by Piotr, and yeah, like, I forgot the other author, but yeah, like it was used there. We have actually used it in a number of papers when we want to compute minimum size clustering. But now I'm going to tell you how we use it in actually building the graphs for a downstream task that maybe clustering is a good application. So what we have developed is what we call stars, which is graph building based on two-hop spanners. The stars algorithm tries to basically like what it does is it does like the locally sensitive hashing step, but when we build each bucket in the locally sensitive hashing technique, instead of building or computing all pairs, we select a leader, let's say, on each bucket, and we only compute basically the similarity scores, maybe with the learning model, from these pairs, from these leaders to each of the points in the bucket. So we go from B squared to B comparisons here. So in a nutshell, like roughly speaking, what we achieve by using the stars and with sorting LSH, for example, we build a graph that has this property that the top k neighbors are not necessarily connected to each point, but they're connected within a path of length 2. And that gives us like the ability to make the graph building part, even the running time, independent of k, which is the top k that we want to compute. And that gives us like big advantages. So this is theoretically impossible to do on the nearest neighbor graph itself. So we have to go to the two-hop neighborhood graph. So we have now, like, we have formal theorems that show the stars algorithm that I'll tell you about actually computes a proper two-hop neighborhood in a distributed way. And the like more details of the algorithm is we first split the points using sorting LSH, and then on each hash bucket, instead of like picking only one leader, we pick n to the 1 over c leaders in a careful manner, and then we compare points only to these leaders. And yeah, like I already told you about what we mean by sorting LSH in general. So maybe in the interest of time, yeah, I have like another topic. So like in order to prove that like this algorithm actually works, we have to like basically make sure that like in each iteration we keep track of the like we can keep the paths of length 2 properly, but then it has like a proper like an issue that we have to solve with a small trick. Yeah, like the proofs are not hard, and actually Rajesh, who built these slides, can help you, can answer questions about the details of this at the workshop. Let me skip that and basically, in the interest of time, tell you about the empirical studies that we have. based on this two-hop spanner. So we can build graphs like we can get maybe 10 to 20x fold reduction in the number of comparisons that we have to do. And these comparisons could be, for example, running these pairs of nodes, like running a maybe costly deep learning model or a random forest model on these like pairs of nodes. So this big improvement in number of comparisons gives us reasonable improvement in the running time of the algorithm. But then the question is, how much do we lose in the quality of the models? And yeah, like we have basically different studies of what's the recall of the top K neighbors. And also if we run a clustering algorithm after building this graph, what's the loss in the clustering quality? And for most of the applications we have, if we fix an LSH technique and then amend it with the two-hop neighborhood version, the quality of the clustering that we get out of the original cluster, like LSH technique, which is much more costly, to the case of solving the clustering problem on the two-hop neighborhood case is like very comparable. So yeah, there are like different pairs of algorithms here that we can see the quality in terms of quality are like very similar. So that's also reported in the paper. So like to just summarize the second part, we developed this two-hop spanner technique that helps us build much sparser graphs that can be used to solve like several downstream tasks like at scale, and in basically provably we can show we can recover the KN graph in nearly linear time, but in practice we also see like big improvements that we report on big data sets. So like some of the data sets that we develop and we analyze in this paper have like up to 10 trillions of edges, by the way. So now the very last part, which is about parallel clustering, which is like maybe one of the most popular parts of the library. So I want to tell you about what we have developed more recently in the multi-core part of the clustering. But first of all, like, let me emphasize that clustering is one of the most applicable tools in the library. We use it for feature engineering. We use it for experimental design, causal inference. We use it, as I said, in privacy and anonymity, enforcing that, and so on. In terms of the type of algorithms that we've developed, hierarchical clustering is the focus of actually this part of the talk. It's actually the most popular technique, most effective technique. But we have metric clustering, clustering with constraint, for example, balanced partitioning or enforcing a minimum size, and community detection type algorithms. And the techniques we use here are message passing, random walks, local search, again, locally sensitive hashing, especially when we get to metric clustering, and also composable core sets. One prominent example is connected components, where we have both distributed and basically multi-core parallel algorithms. But then connected components is very related to what we call hierarchical clustering. And that's what I want to tell you in this part of the talk. What I mean by hierarchical clustering is, as you've seen, maybe like the clustering method that gives us a hierarchy of clusters, and there are like many different sequential algorithms for it. There's a hack specific algorithm that we'll actually talk about more. It's like hierarchical agglomerative clustering. There's single linkage, average linkage, different variants of linkage algorithms. And then there is affinity clustering that we have developed. And it's actually maybe the most popular hierarchical clustering technique that's used in our team. So what is affinity hierarchical clustering? It's a parallel clustering technique that it's like a parallel linkage clustering technique that can be done. Each round of this clustering can be done in one round of MapReduce and distributed hash table service. So what we do is, given the set of edges, we first keep the heaviest edge connected to each node. And then with this, we have actually, like, because each node is connected to the heaviest edge connected to it, we actually form like rooted trees. And by writing these like numbers into a distributed hash table service, we can resolve the each cluster in one round of like map reduce with distributed hash superservice. And this will give us like the first level of clustering, and then we can reiterate and recluster by building a graph over these clusters. So that's how hierarchical, like affinity hierarchical clustering is done. We have some theoretical studies of what are the properties of this algorithm. Even though it looks very simple, it's actually, and we first maybe developed it, I don't know, 7 years ago as a baseline to some of our more fancier algorithms, local random walk type algorithms. This has proved like very useful, and basically it beats like some of the fancier algorithms we had in like many of the applications we had. So then like we developed some theoretical studies of why it performs well. It's basically, it's fine, but it's not as good as some of the other hierarchical clustering algorithms that I'm going to tell you next, and that's more recent. But the more recent algorithms also developed in what we call shared memory parallelism. This is different from the map reduce model that I introduced at the beginning. Let me just emphasize that in this context, we care about the depths of the computation graph that may be done like in parallel in a multi-core system. And our goal is to have an algorithm that the total work is maybe near linear, but then we want to also minimize the depths of the computation graph. And the running time that we compute at the end is the order of this depth, and also the order of the total work and over the number of processors. So the shared memory model is of interest when we have a single machine with very like big like memory and like many processors. And these type of machines are becoming more and more available on the cloud and in general. So for example, we can have like very cost-effective like machines with 72 processors and terabytes of memory. And this is like the reason that we think actually this is very effective, and we have actually ramped up our like algorithmic development in this line of work. Another reason is the paper that Laxman, Guy Block, and Julian wrote a couple of years ago, in which they developed many different algorithms for analyzing big graphs like 220 billion edges on a single machine very effectively. So what we have done in the past 2-3 years is actually to develop some of the clustering algorithms that are more useful for us in this framework that we call GBBS framework. So on the shared memory.
Vahab, just to let you know, you have about 4 minutes. 4 minutes.
Okay.
Thanks.
Sounds good. So I'll ramp up. Yeah. So on the shared memory side, we develop the affinity clustering on the shared memory side, and we can cluster a graph with 100 billion edges in only like 10 minutes. But then what we have done more recently is what we call par-hack or parallel approximate hack that can handle a graph with 100 billion edges in 3 hours. We also developed some new distributed algorithms for hack that I won't have time to talk about. But let me tell you a bit about this par-hack development that has, that we've developed recently. To define par-hack, let me emphasize what I mean by hack. More specifically, the hack algorithm or hierarchical agglomerative clustering algorithm is where in a sequential way, like in a greedy manner, at each step we find 2 clusters. So we start from singleton clusters, and in each step we find 2 clusters that are most similar, and we connect them to each other. Now, in order to define hack algorithm, we have to also define what is the linkage function, or what is the similarity between clusters. And like in a single linkage clustering method, the similarity between 2 clusters is related to the maximum similarity between any nodes. The most popular and most effective way of doing actually this type of clustering hierarchical hack algorithm is what we call average linkage. So average linkage hack is where the similarity between two clusters is the average of the similarity scores between the nodes. And like this way of looking at the hierarchical clustering problem gives us actually the dendrogram of the clusters. So what we have first observed, in order to develop a good parallel algorithm, we have to develop a good a linear time total work algorithm. So we developed an algorithm with n to the m times m to the a square root of m time algorithm for a hack, for average linkage hack. And we have reasons that this is actually the optimal. Now the question is, can we develop a parallel algorithm? We first observed that actually the hack problem itself is p-complete. So we don't hope to develop a polylog depth algorithm for this, but we relax the hack notion to what we call approximate hack. And there, instead of connecting two clusters that are most similar, we connect two clusters that are approximately similar. And that becomes like a definition of what we call approximate hack algorithm. Now the question is, can we implement this algorithm in parallel? And the answer is yes. In the par-hack algorithm, we can actually try to compute all edges that are within like an epsilon, 1 plus epsilon fraction of the optimum similar, most similar clusters. And we have a technique to compute this most similar, approximate most similar thing in a logarithmic number of rounds that I'm going to skip now that I have only 1 minute. So yeah, we can do this by a careful coloring scheme and implementing in a distributed way. I guess what I'm excited about to report is the performance of this algorithm on some big data sets. We have an implementation of it that's now open source. We observe that what we call par-hack achieves actually the highest quality. It achieves higher quality than affinity. Affinity remains the most, the fastest algorithm, but what we call par-hack actually improves on many different distributed and parallel implementations that are out there that are reported in other papers. And then in terms of quality, we report different, basically, we show that the more, the better epsilon, the better approximation actually results in better quality as well. And yeah, it also improves the running time over the sequential version by a big factor. So I guess I'm done now with this, and I skip the distributed parts of the results that are very much under development. These are very recent work that I actually included in this part of the talk. So to summarize, we are developing these hierarchical clustering techniques both in the parallel and distributed way. Actually, the next talk by Sanjeev will talk about some of the distributed algorithms that are also related to some of these techniques. And I know I'm out of time already, 1 minute over. Thank you for your attention.
Thanks, Vahab, for the whirlwind tour. Questions? So perhaps you can tell us a little bit just about this the tera-scale version. What changed qualitatively at this stage when your graphs have trillions of edges?
Oh yeah. So the par-hack algorithm can handle graphs with up to, let's say, 100 billion edges on a single machine. And tera-hack can handle graphs with trillions of edges or 10 trillion, the biggest graph that we have run it on is maybe 10, 20 trillion edges. So it doesn't have any limitation on that side.
Great. Other questions? All right. If not, let's thank Vahab again.